Alright, so this video lesson shows how the sum and the difference identities can be applied in various different situations, in various different problems. So right here, let's look into our first example over here. So on the computer screen, what I have here, let's say we have as an example, let's evaluate the exact value of cosine of 75 degrees by regarding 75 degrees as a sum or a difference of two known angles. So what to realize before we start it here is that this angle here, 75 degrees, is not a known angle on the unit circle. But we can re-express, so the term regarding here means we can re-express 75 degrees here as either a sum or a difference of two known angles on the unit circle. And so now allow me to get back on my writing board here. So allow me to show two different directions of the problem here. Starting with cosine of 75 degrees. Then one way we can see 75 degrees as the sum of 30 degrees and 45 degrees. So that means consequently our cosine of 75 degrees can be rewritten as cosine of 30 degrees plus 45 degrees. And not to mention that this problem here, we are currently working in degrees right here. And so now at this point, once we have successfully put our angle here, 75 degrees, as a sum of two angles, 30 degrees and 45 degrees, what we now realize is that these are the two known angles that we can easily locate on the unit circle. And so at this point, after successfully expressing 75 degrees as the sum of these two known angles, then right here realizing that we have cosine of a sum, then now I can recall that cosine of a sum is cosine of x, provided that the sum is x plus y. So cosine of the sum is cosine of x times cosine of y, but minus sine of x times sine of y. All right, so that is a brief reminder about the sum identities with cosine, because fundamentally what we're having here is a cosine value to be calculated in exact value. And so cosine of, in that way, applying our identity here for cosine of a sum right into this problem, then we can rewrite cosine of this sum as cosine of 30 degrees times cosine of 45 degrees, then minus sine of 30 degrees times sine of 45 degrees. And now each one of these values, cosine of 30, cosine of 45, sine of 30 degrees, and sine of 45 degrees, these are all well-known values among the unit circle. So cosine of 30 degrees is a square root of 3 over 2, positive square root 3 over 2. In product with, so now cosine of 45 degrees on a unit circle is going to be a positive square root of 2 over 2. Then we have a subtraction according to the identity being indicated here. And so now sine of 30 degrees on the unit circle, we can find out that it's going to equal 1/2, positive 1/2. And sine of 45 degrees on the unit circle is going to be square root of 2 over 2. And so now our calculation is ready for action. And so, and now one more time, looking back in the screen itself on the computer here, then the intention of the problem is looking for the exact value of cosine of 75 degrees. So in that way, we will move on with this, or we will proceed with this calculation entirely keeping things in exact expressions, meaning square roots are going to be involved, and we must be able to reduce a square root. And so here I am going to be looking at square root of 3 times square root of 2, but over 4 minus, and now what I'm looking here is a square root of 2 over 4, because multiplying these two fractions together. Now I have my reason for doing this right now. So one way of writing the final answer here is that we can write this first fraction is as a square root of 6 over 4 minus square root of 2 over 4, and brings the answer to one fraction, which is square root of 6 minus square root of 2, all in the numerator, divided by 4. That's one way we can write our final answer. Alternatively, we can also, the reason I left this first fraction as a square root of 3 times square root of 2 without multiplying all together into a square root of 6 here simply is because I would like to make use of that common factor square root of 2 in both terms here. So another way of expressing, we already found the final answer here, but I would like to point out that we can also factor out the square root of 2 over 4 here as a common factor. So we're looking at the square root of 2, and now after factoring out in parentheses, we're looking at square root of 3 minus 1 all over 4. This is another way of how we can write our final answer in exact value. And still, in the same problem here, what if we chose? So really, one more time, looking back at the screen here, the problem really is giving us a choice about either we can express that 75 degrees as a sum, and that's what I just did just now. Now I am about to attempt again, but in a different direction. I am going to re-express 75 here as a difference of two known angles. So in that way, 75 can be written as 120 degrees minus 45. And then this is not the only way, including the way how I wrote the sum, 75 as a sum earlier. This is not the only way. So 75 can be a sum of 30 plus 45, or it can be other sums here. This is right now at this moment when I'm writing this lecture, writing this video lesson, and that's all I can think of right now. But it's all, at this point, it's all about we need to find either, we need to re-express 75 as either a sum or expressing 75 as a difference of two known angles. And so back to what I was in the middle of, then now I'm attempting to write this 75 as a difference of two known angles. So 120 degrees is clearly known on the unit circle, and 45 degrees is also known on the unit circle. And so that means cosine of 75 degrees now in this case can be re-expressed as cosine of the difference 120 degrees minus 45 degrees. And now at this point I need to recall again that we have already learned about the identity cosine of a difference x minus y. So cosine of a difference in the two angles x and y right here, cosine of x and y namely is equal to cosine of x times cosine of y, but add or plus sine of x times sine of y. And let's keep it here now as our reminder, even though anyone viewing this video have already learned this through the lecture or through so many textbooks, standard textbooks for trigonometry. So now applying this identity, this difference, cosine of a difference identity into our problem here currently, then I can rewrite this. I can start writing this out as cosine of 120 degrees, and again we're working in degrees right now, multiply with cosine of 45 minus sine of 120 degrees times sine of 45 degrees. And now these are all these values, cosine of 120 degrees, cosine of 45 degrees, and so on and so on. These are all common values that we can easily locate within the unit circle. And so cosine of 120 degrees is going to be a negative 1/2. And cosine of 45 is also a negative value. Positive value. Cosine of 45 degrees is square root of 2/2. And here we're looking at minus, and now sine of 120 is going to be a positive square root of 3/2. And sine of 45 degrees is going to be also positive square root 2/2. And I must make a correction here that it should have been a plus here. So it's a plus here. And the identity is as according to the identity that's still written right here in front of us. And so now in that way, now we're looking at minus square root of 2/4 by multiplying the two fractions in the first term here together, and plus, and now again similar to what I did earlier, then I'm going to purposely write these two fractions in a product as square root of 3 times square root of 2 without combining square root of 3 and square root of 2 into one square root and over 4. But so now at this point here we realize that the answer came out here just like the answer that came out in the earlier problem, because that is just one problem. It's just a different direction of how we approach it. And so this now I can rewrite as a first term. So, and just similar to how I did earlier, similarly here I'm gonna go one way. I'm gonna rewrite this as a first term, and it's a square root of 6/4 minus square root of 2/4. And we can now bring it all into one fraction by writing it as square root of 6 minus square root of 2/4. And this is our final answer. Alternatively, just like how I have done earlier, I can now see that we have a common factor, and that was my purpose in the beginning, to write the product of square root 3 times square root 2 here without combining them into an overall square root like this, because I would like to show a common factor. So now we can factor out the common factor being square root 2, and after factoring out square root 2 as a common factor, then these two terms remain square root 3 minus 1 divided by 4. And now that's another way of writing our final answer. And any instructor should be able to accept any of these two forms of final expression, the final expression of the final answer. And now in a different example, quite similar to what we have finished earlier. And now in this example, what we have here is telling us to evaluate the exact value of sine of 7 pi over 12 by regarding the angle 7 pi over 12 as either a sum or a difference of two known angles. So admittedly, this problem is exactly the same, pretty much exactly the same as the earlier example we have seen. The only difference now is that we are working in the radians instead of degrees here, and we can still make a choice to express our angle 7 pi over 12 here either as a sum or as a difference. But for this video lesson, I am going to be showing both. And so again, writing down the problem, what we have here at start is sine of 7 pi over 12. Okay, and now I am going to first start out by, my first choice here is to express 7 pi over 12 here as a sum. So I observe that 7 pi is, let's say, how about a 3 pi plus 4 pi over 12. And I actually said how about to indicate that it's just my own suggestions. But anybody else viewing this video can also have a different way to express 7 pi as a sum as well. But now the point here is that once we have expressed 7 pi here as a sum of 3 pi plus 4 pi, then we can go ahead and break down this fraction into two separate terms. So algebraically, we can break it down as 3 pi over 12 plus a 4 pi over 12. And this is going to be, now 3 pi over 12 is reduced to pi over 4, and 3 pi over 12 is reduced to pi over 3. So now 7 pi over 12 is successfully expressed as a sum of pi over 4 and pi over 3. But the good news is that the good usefulness here is that these are some two known angles that we can easily find and locate within the unit circle. All right, and so now to get started into the problem, then once we have successfully written our 7 pi over 12 as a sum, and as I mentioned in the earlier example and including this example as well, expressing this angle into a pi over 4 plus pi over 3 is not the only way to express this angle into a sum. I mean, any viewer out there, if you have enough creativity, you can come up with a different sum of two known angles on the unit circle where it's sum up to equal 7 pi over 12. This is only right now at this moment I can think of. This 7 pi over 12 is the sum of these two angles. So after that observation, and after we have successfully re-expressed 7 pi over 12 into a pi over 4 plus pi over 3, then now our sine of 7 pi over 12 is consequently equal to sine of pi over 4 plus pi over 3. And so now at this point, again, I need to recall that we have already learned, either through the textbook or through a lecture, that there is an identity that's can help us calculate sine of a sum. So sine of a sum x and y here can be equal, is calculated as sine of x times cosine of y, but plus sine of y times cosine of x. And since being a little short at space here, so after writing this down, I'm gonna move my writing board and to get back to the writing space we have been in earlier. But so now applying the identity that we have had here into our problem, then this step, in the next step, this is how I'm writing it. Sine of a sum pi over 4 plus pi over 3. Then according to the sine of a sum identity, we can write this problem here, sine of this sum, as sine of pi over 4 times cosine. But notice in the formula, we switch the sine of x and cosine of y. And sine of y, cosine of x. So sine of x is here, y is here. So sine of pi over 4 times cosine, but of the other angle. So pi over 3. And now I'm going to add. And here we're looking at the next one. The next one here is sine of pi over 3. But I'm going to multiply with cosine of pi over 4. All right, and now the usefulness of writing this angle 7 pi over 12 as a sum pi over 4 plus pi over 3 is that when we come down to this point right here, then we can use the sum identity, and now being different little parts of the sum identity here, then these are all common values among the unit circle, where we can easily locate the value. So now sine of pi over 4 is going to be a positive square root 2 over 2. And then cosine of pi over 3 is going to be a positive 1/2. And plus, now sine of pi over 3 is going to be positive square root 3 over 2. And cosine of pi over 4 is another positive value, positive square root 2 over 2. And so in that way, now again, one more time looking back at the problem on the computer screen, the wording is asking for, the problem itself is asking for evaluating the exact value of sine of 7 pi over 12. So that means in our work here, we have to proceed with all of these square root expressions involved, and also including fractions. So be ready to simplify square roots and be able to work with fractions here. So now square root 2 over 2 times 1/2 is the same as square root of 2 over 4, and we're leaving that in exact fraction, in exact value, exact expression, and that's what it's meant there. And now again, the product of these two fractions, little fractions here, for now I'm gonna write it as a square root of 3 times square root of 2 in the numerator, all over 4. And I have my purpose again to keep this fraction here a little bit inconvenient as a square root of 3 times square root of 2, because for the later step I will be able to branch that out into two different directions. But now, so one way we can express our final answer as square root 2 over square root 4, that comes out from the first term, but plus, so now square root 3 times square root 2 together can be combined into square root of 6 over 4. And now we can put all that into one fraction. So square root 2 plus square root of 6 over 4. And that's one way how we write our final answer. And now alternatively, we can also, and this is now explaining the reason why I left this term here as a a product of square root 3 times square root 2 without combining that into a square root 6 here, because now at least up at this point here, I can see we have a common factor being a square root 2 here. So putting it all together in one fraction, then the common denominator is 4. But in the numerator, after adding these two terms here, and as I mentioned earlier about recognizing a common factor, then we can factor out the square root of 2, and now what remains in the parentheses is 1 plus square root of 3. And that is another way of writing our final answer. And that's how the problem is being done from the beginning to the end right here, and leaving that in two different ways of writing the answer in exact value. And then still with the same problem now, but let's now try it again by expressing 7 pi over 12, the angle here, as a difference. And so at this moment right here, right now, all I can think of is that we can express 7 pi over 12, the 7 pi on top. I can express that as a 10 pi minus 3 pi, because obviously 7 pi is a difference of 10 pi and 3 pi over 12. And that can be broken down into two separate terms again. Now 10 pi over 12 minus 3 pi over 12, and that leads to having two separate terms here being, so now we have a difference of between 5 pi over 6, that's what reduced after reducing this, and then minus 3 pi over 12 is reduced to pi over 4. So now, in other words, 7 pi over 12 can be successfully expressed as a difference of two known angles. 5 pi over 6 is a known angle on a unit circle, and pi over 4 is another known angle on a unit circle. And here we have expressed 7 pi over 12 as the difference of these two known angles. And so now that means sine of 7 pi over 12 is going to be the same as sine of this difference that we have previously found. So 5 pi over 6 minus pi over 4. And so now at this point, again, I need to recall for anyone viewing this video that we have also learned through some lecture or through reading some textbook, some standard textbook, that we have an identity for sine of a difference. So sine of x minus y. So that's why we're having a difference here being inside of a sine function. That is sine of x times cosine of y. Very similar to the sine of a sum. But here we're now going to have a subtraction. Now minus here sine of y times cosine of x. And that completes our sine of a difference identity. And so now applying that, and for the rest of the video here, I am going to leave this here with us. So now applying that identity into our problem here, then we're looking at sine of 5 pi over 6 here is playing in the role of x right here. So 5 pi over 6 times cosine of y, and pi over 4 in this problem is playing in the role of y. So cosine of pi over 4, and now we're going to subtract, and here we're looking at sine. Now I'm going to switch to sine of y right here, the other angle. So sine of pi over 4 times cosine of 5 pi over 6. So once again, before I move on any further, then we can quickly notice that any of these values, sine of 5 pi over 6, the cosine of pi over 4, the sine of pi over 4, or the cosine of 5 pi over 6, these are all common values that we can easily locate within the unit circle. And so sine of 5 pi over 6 is going to be positive 1/2. That's the value from a unit circle. And then cosine of pi over 4 is going to be positive square root 2 over 2. So now consequently I'm having 1/2 times square root 2 over 2. And then the formula says minus, there we go, we're going to minus. Sine of pi over 4 is going to be a positive square root 2 over 2. And then we're going to multiply with cosine of 5 pi over 6 is going to give me a negative value. And this time negative square root 3 over 2. So the reason I can get these values so easily because these are all common values that we can easily locate among the unit circle. And so now again, I'm now going to combine these two fractions into one fraction. So 1/2 times square root 2 over 2 gives me square root of 2 over 4. And these two fractions, but notice there's negative sign multiplied with negative sign, so they become plus. So now I'm going to have square root 2 in product with square root 3. Allow me to once again write it that way without combining these two into one square root and over 4. And so now from that point right here, from that understanding right here, then one way we can express our answer here as, so square root 2 over 4 is what comes out from the first term, but plus, so now all that here, now I can, in the next step, I can go ahead and combine these into one square root, so square root of 6 over 4. And now putting the two fractions here into one fraction, since they already had common denominator, then we're looking at square root of 6 plus square root 2. Now forgive me that I'm swapping the order of the two terms, but it shouldn't matter because here we have adding. So addition is commutative, remember? So, and we divide by 4. So that's one way how we can write the final answer. And then again, alternatively, looking back at this step right here, then we can notice that we had a common factor being square root 2 among the two terms here. So now we can factor out the square root of 2 as a common factor. And of course, we're putting that into one term, one fraction. And then after factoring out the square root of 2 here as a common factor, then first term becomes 1, and the second term has only square root of 3 remains. And now it's 1 plus square root of 3. And that's another way of expressing the final answer. And these two final answers should look exactly like the final answers we have had when we were expressing 7 pi over 12 as a sum of two known angles.